Welcome to the first of the videos over Chapter 4. We have now taken our first exam, and you're transitioning into the middle third of the semester. In this third, we're going to cover Chapter 4, 5, and 6. What are we going to cover over Chapter 4? Well, we are going to cover the different types of reactions. There's 4 different types, and we'll talk about that in a little bit. Then we're going to talk about how we can use those reactions and those different types of reactions to calculate how much of something that can react. So we're going to talk about things like limiting reagents and theoretical yields. We'll also start talking about solutions and what solutions are and how we can use those in our calculations. And then we're going to finally start talking about titrations, how we can titrate an acid with a base. But before we get in any of the math, we're going to start talking about reactions. And there's 4 main types of reactions that we're going to talk about. The first one is a precipitation reaction. Precipitation reactions, as the name suggests, talks about something that will fall out of solution, just like rain or precipitation falls from the sky. The second type of reaction is an acid-base neutralization. The third type of reaction we're going to talk about is a gas-evolving reaction. These are reactions where after the chemical reaction has taken place, a gas is released. And then finally, we're going to talk about a redox or a reduction-oxidation reaction and how we can tell if something is a redox reaction. One of the things that we're going to learn in this section is how can we tell if something is a precipitation, an acid-base neutralization, a redox, or a gas-evolving reaction. So, one of the things that's going to be very important in this chapter, in this section, are states of matter. So here is a balanced chemical equation. You might notice there are state of matter descriptions or descriptors that are found as subscripts. And each state of matter is very important. So there's 4 of them that we can use. S is equal to solid, G is equal to gas, L is equal to liquid, and then AQ is known as aqueous. Aqueous is anything that is dissolved in water. And so if we had an acid, we would put aqueous. If we had an ionic compound, like barium iodide, we would put aqueous. And that denotes that it is in water. So, the 4 types of chemical reactions that we're going to talk about. The first one we're going to talk about is a precipitation reaction. Precipitation reactions have a solid product. So that is how you know that it is a precipitation reaction. Now, here is a table, table 4.1 that is in your book. You do not have to memorize this table, but you should get practice looking at these different types of reactions and using these different rules to determine if there is a precipitate. So how do we use this table? Well, we look on the left column for the ions that are in our compound. In the top 4 rows are compounds that are usually soluble, and the bottom 2 rows are compounds that are usually insoluble. But there are exceptions sometimes to these rules. And so if you have an alkali metal or ammonium There are no exceptions. Every time you see that, it is always soluble. However, if we have, let's say, chlorine, and we'll make silver chloride, right? Silver 1 chloride. That is an exception because silver is in the exception column. So that would be solid. Whereas sodium chloride is always aqueous. It's always soluble. So get practice using this table, looking at different things and the different exceptions, being comfortable with it. You will be given this table on exam number 2. So what do we mean by a precipitation reaction, or how do we know what to do with a precipitation reaction? So we can think of it as AB plus CD going to AD plus BC. This is known as a double displacement reaction. In double displacement reactions, we take B and switch it with D. Now, so our products are now AD and BC. We've switched A or C or B and D with each other. Why can we not switch it this way? AB, or not AB, AC and DB. So why can't we have AC and DB? The reason why we can't have that is because, again, A is usually a cation, C is usually a cation, B is usually an anion, and so is D. So if we put A and C together, and D and B together, that will never work because two things of like charges will repel each other. But if we switch B and D with each other, we now have opposite charges, and so that can work. So let's look at a reaction. We're going to take ammonium chloride, and we're going to react it to iron 3 nitrate. So we're going to take this. So we have A, B plus C, D. So in this type of reaction, a double displacement reaction, we're going to switch B and D with each other. And so what we get is ammonium nitrate plus iron 3 chloride. So the iron does not change charge states in this reaction. So the next thing you need to do, so the first thing is we need to make the switch. But we don't have the states of matter on our products yet. So let's go back to our table. Can you erase all that? And let's remember, so we had ammonium nitrate. So here's ammonium. There's no exception. It will always be soluble. So this is aqueous. Now let's look at iron chloride. Here's chlorine. When it pairs with silver, mercury, or lead 2, the resulting compounds are insoluble. But we have iron 3, not listed as an exception, and so it forms an aqueous compound as well. So if you see a precipitation reaction and you have two aqueous compounds, is that truly a precipitation reaction? And the answer to that question is no. So the answer to this, if you were given on an exam or on a quiz, ammonium chloride reacting with iron 3 nitrate, and you did this and you see two aqueous, the answer would be no reaction. Now you might be thinking to yourself, well, how can that be? how can we have a no reaction? And here's how. This is known as the molecular formula, or the molecular formula, the molecular reaction, to where we see each different element that is in this reaction denoted as its molecular formula. There's another way that we can write this formula, and that's known as the ionic formula. And so in an ionic formula, you write individual ions as they would appear in solution. So this reaction would actually look like this. And don't worry about balancing it, because we have not, there won't be any reaction. And so if there's no reaction, you don't have to balance it. The other thing you will notice is all subscripts that are found either outside of polyatomic ions or individual elements move to the front, and that helps balance the charge. Now, this is the complete ionic formula for this reaction. So every time you see an ion, it is now separated because it is dissolved in water, and strong ionic bonds dissolve in water. If you do not believe me, take some salt at dinner, pour it in a glass of water, stir it around, and you will see it dissolve. So, this is the ionic formula. We can make the net ionic formula. So, the net ionic formula looks at what's known as spectator ions. So spectator ions are those that, as the name suggests, just sit back and watch the reaction take place. And so the way we know if it's a spectator ion, if we see the ion in the reactants as well as in the product. So an example would be ammonium. It's the same on both sides. We see chlorine, same on both sides, and iron and nitrate. Now, what is left over? The obvious answer is nothing. And this is why if you do not form a solid in a precipitation reaction, you do not have a reaction. So, step one, step number one, when you're given a reaction and you know it's a precipitation reaction or a type of precipitation reaction, you need to check if a solid is formed. If no solid, then you write no reaction and you're done with that problem. You can move on. If there is a solid, the second rule then is you need to balance the equation. So, if a solid, you need to check if a solid's formed. If it's not formed, then there's no reaction. You're done with that problem. You can move on. Step number two is that if there is a solid, then you need to balance the equation. Let's look at another example. So we have sodium hydroxide, aqueous, plus copper 2 bromide, aqueous. So again, here we have AB plus CD. So we're going to switch B and D. So we're going to make copper 2 oxide plus sodium bromide. Now, it does not matter what order you place your products. If I put sodium bromide plus copper 2 oxide, that doesn't matter as long as they're both present. So, let's go back to our table. Well, we know we have a compound with sodium, no exceptions. That's always going to be soluble. But we also now have a compound with a hydroxyl group on it. So, hydroxyl group, when you pair it with lithium, sodium, potassium, or ammonium, they're soluble, per rule number 1. They didn't pair. We have it with copper 2. So now we look down here. Calcium, barium, or strontium. It's slightly soluble, which still means insoluble. So, since we have copper 2 hydroxide, we know that's a solid. Sodium, as we saw on the table, is always soluble, so that will be aqueous. So now let's look. We won't pull apart the ions, but let's look to see the net. Oh, I'm skipping a step. We will find the net ionic equation, but if we have a solid, what was the next step? And that is to balance the equation. So to balance this equation, we have 2 hydroxyls on this side. We'll have 2 hydroxyls on this side. And so now we have 2 sodiums and 2 bromines. So now we're balanced. So, what is the net ionic equation? So we know anything that is aqueous will break apart into its ions. And then all we have to do is see what will go away. So sodium and sodium, because they're going to be in their ionic form. And then you have bromine and bromine. It doesn't matter how many bromines you have, as long as the ion is the same, it'll get canceled out. So the 2 spectator ions in this reaction are sodium and bromine. So then the net ionic equation, and I usually just put the cation first, just because that's the way it looks in the ionic compound. And then we can make the ions aqueous. So there's the net ionic equation for reacting sodium hydroxide with copper bromide, or copper 2 bromide. So a precipitation reaction has a solid product. So what about acid-base neutralization reactions? Acid-base neutralization reactions always yield you the same 2 products. So you have acid plus base yields you salt plus water, which gets a liquid. It doesn't matter what acid and base you have, it will always be solid or salt plus water. So here's hydroiodic acid, and we're going to add base, barium hydroxide. So how do we know if it's an acid? Just like with our naming, it has a hydrogen in front. But how do we know if it's a base? The other portion of the reactant has to have an OH. And then if you notice, we still have AB plus CD. So all we do is we switch those 2 things, and we said we get barium iodide, so that's our salt, plus water, aqueous and liquid. We will not write net ionic equations for strong acids, strong bases in the neutralization, and the reason why we're not going to do that is because it's the same. It's always H plus OH minus goes to H2O. To know if something is a strong acid or a strong base, I would recommend looking at and being familiar with Table 4.2. Table 4.2 details strong acids and bases. When we get to class, we'll talk about what it means to come apart, to dissolve in water, and what that actually means. Now, I've written an equation here, but we're still not done. We have to be sure that everything is balanced. Since we're not going to do a net ionic equation, acid-base neutralization will always occur. So to balance this equation, so we have 2 iodines over here. Now we have 2. And so we have 4 total hydrogens and 2 total oxygens. and so we put a 2 over there. So now we have 4 total hydrogens and 2 total oxygens on the product and reactant sides. And so this is acid-base neutralization. Whenever you see a hydrogen in front and we add a hydroxyl group to it, we're going to neutralize that acid with a base. And so we make a salt and water every single time. The next type of reaction I'm just going to cover very briefly is known as a gas evolution reaction. So some molecules, when you make them in a chemical reaction, will decompose into a gas. We really won't be tested over this in class, but you will have to be aware of this in the lab. And table 4.3 will be another help on different species that'll decompose. And so let's look at an example. Ammonium chloride plus sodium hydroxide. So this is not an acid-base chemical reaction. And the reason is because this is not an acid. This is a base because it's got the hydroxyl group, but what we're reacting with is not an acid. And so it'll still be a little bit different. But what you know is you have A, B plus C, D. So we're going to, again, switch A and B, or we're going to switch B with D. When we do that, we get ammonium hydroxide plus sodium chloride. Now, if you were to look at this compound in table 4.3, it will tell you that it will decompose. When it is in the presence of water and when you have it, it decomposes into a gas. And the gas it decomposes into is ammonia. It also decomposes to water. And we still have the sodium chloride. And so you can see how this has now decomposed and broken into that. And like I said, you won't be tested over these types of reactions, but you should still be familiar with them enough to recognize it, as well as to use it in the labs. So the last type of reaction we're going to cover, so the precipitation was a pretty big deal. The acid-base is still a pretty big deal, but it's a little bit simpler. And then gas evolution, we're not really going to talk into much detail, but then we get reduction-oxidation reactions. And these actually change what's the charge states of the elements in the reaction. We've already started talking about charge states, but we're really going to talk about it in more detail in this chapter. So there's actually 3 types of redox reactions. One is a synthesis. So we take 2 elements and we put them together to make a compound. Sodium chloride, hydrogen and oxygen. That would be a redox reaction. And I'll show you why when we start talking about charge states. The other thing is decomposition. When we take a molecule like water and we break it into its oxygen and hydrogen elements. And then we have a single displacement. And so we are used to seeing AB plus CD goes to AD plus AB plus CD going to AD plus CB. Here what we have is A plus BC. So this is going to be the cation, this is going to be an anion. And what we do is we trade A with B. And so now we have B plus AC, where A now becomes the cation, and C still stays the anion, right? That's single displacement. So we're going to talk about and see a couple of these different reactions as you guys practice. So, how do we assign oxidation states? How do we know what charge something has? Rule number 1, and they always go in this order. The oxidation state of an atom in its free element is 0. So things like magnesium solid, copper solid, hydrogen gas, right? Anything that is its element is 0. The oxidation state of a monoatomic ion is equal to its charge. So let's say we had a sodium +1. The charge state of that element, that ion, is +1. The sum of the oxidation states of all atoms in a neutral molecule or formula unit is 0. So if we had sodium chloride, the total charge has to be 0, which is why sodium is +1, chlorine is -1. That's why we use the subscripts. If you have an ion, so let's say nitrate, has a -1 charge, the overall charge of that compound or of that ion has to be a -1. Oxygen, we said, was -2, so -2 times 3 is -6. So to get a -1 charge, N has to be +5. And we're going to do a lot more of those calculations as we practice redox reactions. Group 1, this is an important one that we started learning with naming. Group 1A metals, the alkali metals, always have an oxidation state of +1. And group 2 metals, which are the alkali earth metals, always have an oxidation state of +2. We should know that. So every time you get a periodic table, above group 1A you should always put +1, and above group 2A you should always put +2. And then, so let's say we have sodium oxide. So we know sodium, because it's an alkali metal, is always +1. Since we have 2 of them, we know the total charge of sodium is a +2. So now we have to account for the anion charge, right? Because total charge has to be 0. So that's oxygen -2. Right? So in their compounds, nonmetals are assigned oxidation states according to the table, which I'm going to show you. And then again, it goes from top to bottom. But use context. Use what you know. Know that all alkali metals are always +1 and alkali earth metals are +2. And use that to help you guide and calculate other charge states. So, the oxidation state of any given element generally depends on what elements it's combined to. The only exception, right, because, here's the exception, Rule 4 is greater than Rule 5. It comes before Rule 5. So alkali metals are always +1, alkali earth metals are always +2. Rule number 3 must always be followed. Neutral charged compounds have a 0 overall charge. Ions have that total charge. When assigning oxidation states to elements that are not covered by Rules 4 and 5, such as carbon or nitrogen, sulfur, all of those, we look over at this table. Fluorine is always a -1. Hydrogen is always a +1. Oxygen is usually always a -2. Notice I say usually always. It can change, again, because look at how low it is on the list. Halogens are usually -1, and then group 6A, which is 1 over, is usually -3. Group 5A, which is nitrogen, is usually -2 for group 6A and -3 for group 5A. Again, with more practice, with seeing this a lot more, the better we'll be at it. So, let's look at a reaction. So we have magnesium solid plus H2O. Now, we said this was a single displacement reaction. So A plus BC. We said B is the cation, C is the anion. So if you ever have a doubt of how the single displacement works, think about the charges. So it's always a cation plus an anion. I know this is a molecular compound, but when we do charge states, we'll see it goes cation, or positive charged element, charge state, with a negatively charged state. So which one would magnesium more likely be, a positive or negative? If you say positive, you are correct. So we have magnesium will take the place then of the oxygen, so let's think about this. Because what are we going to put here? We could put an O, and that would be good. But what would we put over here? So let's think of water in a slightly different way. Let's think of water like this. And if we think of water like this, then we can think of this hydroxyl group as being the anion, and this hydrogen as being the cation portion, or the positively charged portion. And so if we think of water like this, which is how we need to think of water, magnesium would then be bound to hydroxyl group, which is a -1 charge overall. We have 2 of those because magnesium is an alkali earth, it's always +2. But then what are we going to be left with? Well, we're going to be left with hydrogen, but again, we said hydrogen is a diatomic element, and so it would have to be H2. And don't forget your units, or states of matter. So aqueous and gas. So, we have just made this reaction. How do we do charge states? So let me erase this. And here is a tip on how you can determine if something is a redox reaction. Redox reactions, if you see an element or 2 elements, you know this is a redox reaction. Because according to rule number 1, what is the charge state of elements in their elemental form? It's 0. And so you know if they start at 0 and then they get put into a compound, they have to change their charge states, which is by definition a reduction-oxidation reaction. So, we can start with, let's start with oxygen, because oxygen rarely ever changes. So there's a -2, there's a -2. Let's do hydrogen, because again, hydrogen rarely ever changes. And hydrogen is usually +1. Now, what you might be looking at this hydroxyl group and think, well, wait, Dr. Bishop, this has an overall charge of -1. And you would be correct. If you look at table 3.4, you'll see that hydroxyl, OH, has a -1 charge. So this makes sense. So we have 2 -1 charges for a total of -2. So magnesium, to balance that out and neutralize the charge, has to be a +2. So, what was oxidized and what was reduced? So we can break out our little mnemonics. So these are the 2 that I use. So we have oil reg. So oxidation is loss of an electron, reduction is gain, or loss of electrons is oxidation, gain of electrons is reduction. It's the same way, just depending on how you want to see it, but they both tell you the same thing. So if you lose an electron, so let's say you start at 0 charge and we lose electrons. What happens to our total charge? We become more positive. Let's say we're at a 0 charge and we gain electrons. What happens to our total charge state? It becomes more negative, right? So when we're looking for things that are oxidized, we want to find something that goes from a 0 or a negative charge and moves to a more positive charge state. So in this reaction, magnesium goes from 0 to +2. So it's losing its electrons. So that is the thing that is oxidized. If you have an oxidation, you have to have a reduction. They have to happen at the same time. So what becomes either more negative or more towards 0? Well, the hydrogen was a +1 and now it's 0. So hydrogen is reduced. We can also find out what is the reducing agent, so what causes the reduction, or the oxidizing agent, what causes the reduction. And what you see is it goes a little bit backwards. The thing that is oxidized is the reducing agent. The thing that is reduced is the oxidizing agent. Oxygen and hydrogen are great oxidizing agents. Metals are great reducing agents, right? Because they want to give up their electrons. So remember, we need to learn these rules for assigning oxidation states, and we need to practice looking through different problems, trying to find different ways that we can calculate charge states, and we'll do it in class. We'll practice in class. But the other tip is, how do we know something is a redox reaction? We look for elements. If we see an element, we know it's a redox reaction. How do we know something is an acid-base neutralization? We look for an acid, we look for a base. So, for Friday, September 14th, I want you guys to get some practice doing some of these reactions. Because once we can figure out reactions and write a balanced equation, then we should be able to go forward. So, I came back to this. This reaction is not balanced. We have 4 hydrogens, 2 oxygens. So all we have to do is put a 2 in front of the water. We have to make sure we have a balanced equation. These equations, this reaction, will help us with our calculations that we'll do in the next video. So for Friday, September the 14th, I want you guys to do and turn in before class number 75, A through D, number 85, A through C, and then number 93, A through F, and 97, A through D. I know it might seem like a lot, but just like with naming, we need to constantly work on naming. We need to now start constantly working on seeing reactions and being able to complete them and to classify them. If you have any questions as you guys go through this, please come see me. We're going to get into some things that will stretch us a little bit, and that's a good thing because that's how we learn. But at the same time, sometimes we can get really confused. And so if you ever are confused, please come see me and I will help you. I hope you guys have a great day.